Let's take a look at how to approach the probability of at least one. And in doing so, the first thing we want to recall is our complement rule, and that is that the probability of A plus the probability of a complement is equal to 1. And additionally, from that, we got that the probability of A is equal to 1 minus the probability of A complement. Okay, so we're going to use this to help us solve at least one problems. When we talk about at least one, that means one or more. So in a second, I think we're going to look at a problem that has to do with a family and the number of girls born in this family of 5 children. If we say at least one girl, that would be one girl or 2 girls or 3 girls or 4 or 5 girls. All of those would be a part of at least one. But what's the complement of at least one? Well, in the case with the girls, the only thing that could happen for a family of 5 children that is not at least one girl would be 0 girls. So the complement of at least one is 0, or of whatever it is we're looking at. So I say 0 of the same type. Okay, or we could say none, right? So a rule for dealing with the probability of at least one type problems is the probability of at least one equals 1 minus the probability of 0 of the same type. Okay. Okay, why do it this way? Well, considering again the example with the number of girls born in the family of 5 children, it might be easy to calculate the probability of 5 girls. That would be pretty easy. But to calculate the probability of exactly 1, and then the probability of exactly 2, and the probability of exactly 3 and 4, and then additionally the 5, that'd be a lot of work. So instead of having to calculate all of those things, what we will do is calculate the one thing that's not included in at least one, and then just subtract that from the total. And that's going to leave us with the probability of at least one. Let's start with a pretty simple example. It says provide, well, the same example that we were just talking about. Provide a written description of the complement of the given event, then find the probability of the complement of the given event. Okay, so our event here is a couple has 5 children. None of the 5 is a girl. So event G is no girls in 5 children. Well, the complement of this is at least one girl in 5 children. Okay? All right, so that's the complement. So how would I solve this? I'm going to look at the probability of at least one girl, okay, of 5 children, okay, and we're going to use our rule. So I'm going to say 1 minus the probability of 0 girls of 5 children, okay? Well, if we had 0 girls, then we must have had 5 boys. Okay? All right, think about that for a second. If we're talking about at least one girl, the only outcome that would not include at least one girl would be all boys. Okay? And so now we need to calculate the probability of having 5 boys. And this is where the multiplication rule comes in. Okay, we're talking about the probability of a boy and a boy and a boy and a boy and a boy. We need 5 boys. Okay, we're using keyword and that lets us know to multiply. And then we need to ask ourselves, are the events independent? And of course they are. Okay, the probability or the likelihood of you having a boy on your second child is not affected by the fact that you had a boy for the first. So the probability is going to be 1/2. They're independent. We're going to have 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Or we could have said 1/2 to the 5th power. And so 1 minus 1/2 to the 5th power is going to give us 31 over 32. Okay? So the probability of at least one girl is going to be 31 over 32. And if you were to list the sample space for a family of 5 children, how they could have boys and girls, you would see one, that there are 32 different possible outcomes, and 31 of them would include at least one girl. All right, let's try this again. At least one is going to be one of our new keywords, and if you're doing the extra credit assignment for Chapter 2, you should definitely include a branch for at least one type problems. But sometimes the problem may not say that exactly. So here it says a statistics student plans to use a TI-84 plus calculator on her final exam. From past experience, she estimates that there is a 0.92 probability that the calculator will work on any given day. Because the final exam is so important, she plans to use redundancy by bringing in 2 TI-84 plus calculators. What is the probability that she will be able to complete her exam with a working calculator? Okay, so first thing I like to do is focus on what the question is asking me to find. And so we're looking at the probability that she will be able to complete her exam with a working calculator. Okay, again, those words don't fit any of our keywords, but when I think about it, in order for her to finish with the working calculator, okay, either one of them is going to work or they both have to work. So I could describe that as at least one. So I'm going to write probability of at least one working calculator. Okay, and so now that we're talking about the probability of at least one, the way that I handle that is 1 minus the probability of 0 working calculators. And so if 0 of them works, then that means that they both fail. So the first calculator breaks down and the second one breaks down as well. Okay? And so now I'm at the point where I can clearly see how I'm going to use the multiplication rule. And I have to ask myself, are the events dependent or independent? Well, hopefully, if she really is intending to have, kind of a backup, then the first calculator working or the second calculator working doesn't need to depend on whether or not the first one works. So really, they need to be independent. So we're going to, if this is really a good plan for redundancy, then we need to have 2 calculators that are independent of one another. Okay, so we get 1 minus the probability of failure, and that's going to we're going to multiply that by the probability of failure. So it's going to be probability of failure squared. Or you could write it as probability of failure times the probability of failure. Okay, now we know that the probability that the calculator works is 0.92. So again, using the complement rule, the probability that the calculator fails to work is going to be 1 minus 0.92 or 0.08. Okay, so the probability of failure, we get 1 minus 0.08 squared, or 0.9936. All right, let's take a look at another example. It has been found that 40% of all people over the age of 85 suffer from Alzheimer's disease. If 3 people over 85 are selected at random, find the probability that at least one person does not suffer from Alzheimer's disease. Okay, so focusing on the question that's asked here, we want to find the probability that at least one. Okay, that's my keyword here. So I'm already coming up with a plan for how to answer this question because I know what to do with probability of at least one problems. So we're talking about the probability at least one of 3 does not suffer, so I'm going to say is well. All right? And so the complement of that is that 0 of 3 is well. So if 0 of the 3 are well, then that means all 3 have the disease. Okay, so we're talking about disease and disease and disease. And the question we need to ask ourselves is, are these dependent or independent? And we will treat them as if they are independent since we're given this percentage, and that percentage should have been based on a very large number. Okay, so we're going to have 0.4 raised to the third power, or 1 minus 0.4 raised to the third power. We get 0.936. All right, in this example, it says, according to FBI data, 12.4% of burglaries are cleared with arrests. A new detective is assigned to 5 burglaries. What is the probability that at least one of them is cleared with an arrest? Okay, so again, I see my key word. We're talking about the probability of at least one. Okay, and so I know how to handle that. Probability of at least one is equal to 1 minus the probability of 0. And of least one of what? At least one is cleared, okay, with an arrest. Okay, so the complement would be that 0 are cleared, okay, with an arrest. Okay, and he's looking at 5 cases, so if 0 are cleared, then that means we have 5 cases that are still open. Okay, so we're talking about the probability of a case that's open, and another that's open, and another that's open, and 2 more that are open. Okay, again, we're given a percentage, and this percentage should be based on a law or based on a large number of observations, and so we're going to treat these things as if they are independent. So we got 1 minus the probability of open, okay, times the probability of open. We'd have that with 5 factors, or the probability that the case is not cleared with an arrest is still open. We're going to raise that to the 5th power. Okay? The probability of clearing it is 12.4%. So the probability that it's not cleared or still open is 100 minus 12.4, or 87.6%, or 0.876. Okay, so we're going to do 1 minus 0.876 to the 5th power. Okay, let's look at what this looks like on our calculator. 1 minus 0.876. I'm going to use this little house top to raise it to the 5th power and hit enter. We get 0.4842 approximately. Okay, so the probability that at least one gets cleared is 0.4842. All right, in part B, it says, what is the probability that the detective clears 5 burglaries with arrest? This is no longer an at least one type problem. We're just interested in the probability that 5 are cleared. Okay, and so when I think about my keywords, we would have cleared and cleared and cleared and cleared and cleared. We're using keyword and that's going to indicate the multiplication rule. So we've got the probability of cleared. Okay, again, we've already said that these events will treat as if they are independent. So this is going to be the probability of cleared to the 5th power. Okay, or 0.124 to the 5th power. And when I do that on my calculator, it gives me 2.931, some other digits, e to the negative 5, or times 10 to the negative 5. Okay, because this is in scientific notation and the exponent is negative, I need to move my decimal point 5 places to the left. So if I do that, we would get 0.12345 Okay, the decimal was here, and if we move it 5 places to the left, we get 1, 2, 3, 4, 5. Okay. So a very, very, very small chance that the detective would clear all 5 of the burglaries with arrest. Okay. In part C, it says, what should we conclude if the detective clears all 5 burglaries with arrest? Okay, well, what we calculated was that would be highly unusual. If this detective was able to do that, then we could say, you know, he's exceptional. He did something that was not very likely to be done. And so it might be fitting to give him a promotion or a raise because he was able to do what was clearly not commonly done. All right, we've talked a lot about birthday data. We've all been engaged in collecting some of that data in one way or another. And in particular, we've been interested in the probability that at least 2 people would have the same birthday. Okay, now you might look at this and say, well, this isn't at least 1, it's at least 2. But I think we'll be able to write this as an at least one type problem. Okay, so we've got 25 people in a class. We're interested in the probability that at least two have the same birthday. Well, if two of them have the same birthday, that means we have a match, right? So two of them having the same birthday is the same thing as saying at least one match. Okay, so that's what we're looking at. And the way that I'm going to calculate this probability, because it would be very difficult to calculate it head on, we'd have to look at all the possibilities of exactly one match, and then possibilities of exactly two matches, and possibility of exactly three matches, and then even possibilities where we had, let's say, multiple matches. Let's say two people had a match on one day and two people had a match on a different day. Okay, it would be just about impossible to calculate this without using this at least one rule. So what we're going to do is 1 minus the probability of 0 matches. Okay, so if we have 0 matches, we've got 25 people. Let's start with the first. Because he's the first, it doesn't matter which day his birthday is. He can choose, or not really choose, but his birthday could be any day of the year. We don't have a problem with that because he's the first. However, if the second person is not going to match the first, then there are only 364 days out of 365 that would work for that. And then 363 days. So we don't want the third person's birthday to match the first or the second. So 363 over 365 and so forth, all the way down to 341 over 365. Okay, and we could use some tricks to calculate that on our calculator. I won't spend time telling you about those tricks, but we would get 1 minus 0.4313 or 0.5687. Okay, so the probability of having at least two people with the same birthday in a group of 25 people is a little more than 50%. Okay, and you might not have thought that, but it's not unlikely. So we were able to get to that by using this rule for at least one and complements. All right, we've got two more examples we want to look at. In a lab, there are 8 technicians. 3 are male and 5 are female. If 3 technicians are selected, find the probability that at least one is female. Okay, so I see my keyword probability of at least one. Okay, of 3 is female. Okay, and so I'm going to use 1 minus the probability that 0 of 3 is female. Okay, so if I have 0 that are female, then that must mean we have 3 that are male. Okay, and so we're talking about male and male and male. Okay, in this case, though, we have a small sample size. There are only 8 technicians. So if I take one out of the pool, it changes the pool significantly. Okay, so these events would actually be dependent. So the way I'm going to calculate that is 1 minus the probability that the first is male is 3 over 8 Okay, I take him out, he's gone. The probability that the second is male, given that the first was male, is 2 over 7. And the probability that the third is male, given that the first and second were male, would be 1 over 6. Okay, if we do that, we get 1 minus 1 over 56, or 55 over 56. Okay, this last problem is very similar to the previous one. We've got 5 instructors who are chemistry instructors and 6 that are physics instructors. We've got a committee of 4 instructors that needs to be selected. Find the probability of at least one being a physics instructor. Okay, so probability of at least one physics equals 1 minus the probability of 0 physics. Okay, so since we have a committee of 4 instructors, that must mean that all 4 of them are chemistry instructors. And so we get 1 minus the probability that the first is a chemistry instructor, okay, times the probability that the second is a chemistry instructor, given that the first was, times the probability that the third is a chemistry instructor, given the first and the second, times the probability that the fourth is a chemistry instructor, given the first, second, and third were all chemistry instructors. Okay, and so the probability that the first one is a chemistry instructor is going to be 5 over 11. Okay, we take him out, he's gone. All right, we multiply that by 4 over 10, because there are 4 chemistry instructors left, 10 total left. Okay, take him out, then 3 over 9, and 2 over 8. Okay. Okay, on our calculator, we would get 1 minus 5 times 4 times 3 times 2 divided by 11 times 10 times 9 times 8, or 0.9848.